Hi, and welcome to the final video in our series on proof, and in this one we're going to be looking at something called proof by counterexample. So we've done deduction and exhaustion, we've got the one left to do, and to be honest this is the easiest one of the three. Proof by counterexample works by the fact that a lot of mathematical statements are very precise. So it's saying like all numbers obey a particular rule, or all types of a particular number obey a rule, and if we can just find one that doesn't, then we can say that that statement isn't true. So here we go, a very simple example. Says, okay, there's our conjecture, all prime numbers are odd. And the key to this fact, it says all prime numbers are odd. And clearly, as we know, we can find the counterexample to this because 2 is a prime number and it's even. So the statement all prime numbers are odd is clearly false because we've been able to find one example where that statement is not true. So we can say, therefore, that our conjecture that all prime numbers are odd is false by counterexample. Really straightforward stuff. Now, it would be nice if everything was simple as that, but it isn't always, so let's just have a look at another one. Here we go. So we've got a conjecture, we've got n squared plus n plus 41 is prime for all values of n. So it might be we start off at this and say, okay, let's just see what happens. So we chuck in n equals 1, 43 is a prime number. N equals 2, 47 is a prime number. And so on. And so we might be looking at this thinking, yep, okay, it seems to be working. I'm struggling to find a counterexample. And as we saw earlier on in our proof by deductions, if you have to go through and try and check every single possible value, you're going to be there a very, very long time. But in this particular case, there is a bit of a shortcut to it, because if we pick, for example, n equals 41, and in all of these kinds of ones, if you just kind of pick that number on the end, the reason is, let's just have a look at what's going to happen. If we put in 41, we've got 41 squared, n is 41, and then there's the 41 on the end, and work it all out, we've got 1763, and we've got to figure out, well, is that thing prime? Well, let's just do a little bit tidying up on the left-hand side. So I've got 41 plus 41, so I've got potentially 41 squared plus 2 lots of 41. Now, again, let's just do a little bit of tidying up. So what I'm going to do is factorize, because I've got, where's my cursor gone? Here it is. I've got a 41 there, and I've got a 41 in there, so I can write this as 41 bracket 41 plus 2, because there's my 41 squared, and there is my 2 lots of 41. All right, and so, but of course, inside that bracket, that is clearly 43. So what we're now saying is 1763 has got two factors, 41 and 43. So clearly, it's not prime. So there's our counterexample. So we can say that that conjecture is false because we've been able to find a counterexample. Okay. Last thing that I just want to mention within this section on proof is sometimes you can end up with a proof that looks really convincing, but is actual fact not all there as it should be. So here we go. This one's an absolute classic. I love doing this one. Here we go. So what we're going to do is, if we start off with A and B and say, okay, let's let them both equal 1. What I'm going to do now is just play around with this expression, and you'll see where we're going to end up. So we've got A equals B. I'm going to multiply that equation by A, giving us A squared equals AB. Nothing wrong with that so far. And then I'm going to just do a bit of subtracting. So I'm going to take B squared off both sides. So you end up with A squared minus B squared equals AB minus B squared. Do a bit of factorising. Factorise it on the left. We're getting A minus B, A plus B. Factorise on the right. Take out the B. We've got B bracket A minus B. Okay. Now let's do a bit of dividing. So I'm going to divide both sides of this by the A minus B term. So divide there. So we're going to get a bit of cancelling going on. There they go. Cancel out on the left and the right. And now we've got something that says A plus B equals B. And by now we should be starting to think, hang on, something's not particularly making sense here, because if A and B are both 1, then we've now got a statement that says 2 is the same as 1. Ta-da! Yeah, now, clearly something is not right with that, because clearly 2 is not equal to 1. But it's very impressive that we can algebraically prove that it is. But what it means is there's something that's not right in there. So, can we spot where the error is? Well, let's say so. If you want to pause the video and have a bit of a think about where you think where the problem might actually be. And if you spotted it, what it is, it's actually happening there. Because if we're saying that A equals B, then that thing there, A minus B, is actually 0. So what we're saying is that in this step here, when we do this divide, we're actually dividing by 0, which clearly is undefined, which means that proof is just not worked because we've got an inherent issue built in within the proof, which is why it ends up with a result that clearly down here is not true. But it's still fairly impressive if you can stand up in front of the class and just demonstrate clearly using a bit of algebra that 2 equals 1.